Okay. Guess we're to optimized aggregate for concrete. Started. Why are we doing the aggregate optimization? This is a pilot specification is out there for the districts to do a couple of bridge decks this year, see how it goes, and then make changes as we need to, and make a permanent spec. The aggregate enhances the packing of the aggregate in the mix design. Reduces shrinkage, reduces permeability potentially, and improves durability. Also, it it makes the mix more able to be vibrated and more stable once you take vibration away. That's kind of the idea, where if it responds to vibration, fills in the gaps, you don't get the mix, because a coarse mix will voids in it, be hard to close up. These mixes tend to not have those problems. So, kind of give you an idea of the shrinkage reduction. One of the other things of this is that you tend to need less cementitious in the mix to get the same strength and stuff. So, kind of idea, shrinkage reduction, biggest shrinkage contributor of the mix. Normal concretes you see with this dark blue line here shrinks about much, and then the optimized aggregate concrete will shrink less because it has a lower cementitious requirement. And this is the chart that we all kind of hopefully have seen by now. There are 7 zones on here that I'll go through. This is from the program that John Swalligan wrote. It's a pretty nice program, and I'll demonstrate that a little later. Now, zone 1 of that chart indicates mixes that are gap graded, potential for segregation, and they'll crack, blister, and spall more, and skin more likely to do that. This is where your typical AAA in Pennsylvania has historically been, in this gap graded area. Zone 2 is kind of where we want to be. Generalized zone 2 indicates an optimum mixture for concrete. Normal maximum aggregate sizes of 2 inches to 3/4 of an inch. Mixtures generally consistent, high quality concrete. This is, we'll talk more about the various zones. Obviously, there's a whole bunch of stuff inside of there. We'll look at the various zones in a minute here. Zone 3 indicates optimum mixture for maximum nominal aggregate size is smaller than 3/4 of an inch. This is where your number 8 mixes would end up playing. Kind of mixtures are a little less stable. Once vibration is taken away, they vibrate very well, but once vibration is taken away, they're not quite as stable. You don't want to put them, if you put them in thick on a slope, you have a chance of them sloughing on you. Zone 4 indicates excessive fines, high potential for segregation, consolidation, and finishing. Mixtures are likely to have high shrinkage, cracking, spalling, and scaling. These are high-order mixes, not really suitable for bridge decks. Zone 5 indicates excessive amounts of coarse aggregate, and intermediate aggregate is not plastic. These are very coarse mixes. Don't tend to close up very well. Real hard to work with. Zero is kind of this anomaly. It's a combination of round and cubical aggregates, hard to keep in balance. It requires extraordinary control of your aggregate stockpiles to keep them from segregating. And here's a kind of a synopsis of what I just went over. I mean, on the upper side of you have excessive fines, and then you have gap graded and rock graded and log graded. Give you an idea. Makes a little reference of what we talked about. Sections within Zone 2. On 2.1, there's several kind of rectangular sections going up Zone 2. Zone 2.1 similar to 0, which is hard to getting toward the well graded, but hard to control the stockpile. It's similar to 0, except that it's a little more flexible. Zone 2.2, it's actually for slip form construction, good particle shape, with good particle shape, aggregate control. But this is more of a where your concrete pavers might have a mix down in here, but it's going to be a little harsh for the deck concrete, and you're not going to. And it's very more. It's also more difficult and near impossible in some cases to pump. Zone where you're getting up into the area where you can slip form in this area, but you can also pump bridge decks. This is the area, which is why this is where our required zone is. Anyhow, but this area here is a little harsher than some might like, but it's a good workable mix. Zone 2.4, sound good mix, good area to be in. Includes placement of vertical construction. This is just generally aggregate. In Zone 2.5, this zone you start getting into a little more than you really to have for shrinkage purposes in the mix, and it's more for hand work. If you really have something you have to place by hand, not necessarily. When they talk about hand work, they're talking about placing by hand, not finishing. But if you have something placed by hand, you might want to be a little up in this area. So, again, just of the areas surrounding, and then the area into what the various things, various areas called up for reference. There are circles within Zone 2 also. The Zone A is, kind of gives you a little idea here. It's the slip forming is better in this area. The circle E is more of a form in place area, and circle C is, where you would it says hand work, but that's more like hand placing. So, if you can kind of tailor your mix to what you're doing. Okay, and then there's the block that is required. Kind of a good base to have generally good concrete that takes into account all of the areas that I just went through. Again, typical AAA is over a gap graded area. Okay, typically, there's a 45 power chart and the 8 to 18 chart that are also required when producers submit their mixes. This is what a typical AAA mix right now, a gap graded mix would plot at. You can see here you're kind of low on the 3/8, and you're kind of below the zero voids line, kind of far away from it. And the 818 chart similarly plots, most of the finer plot below the 8 line, and get this big spike up to 30-35% on the quarter sieve, indicating a gap grade mix. Not really where we want to be. Kind of gives you an idea. These are plotted simply to give you an idea of, well, if you're having problems making it where you're would be. And this generally I just include this slide because it shows you where the next this 45 power chart comes from. Something that's right in the center of the box. Green will always drop outside of the tolerance line, approximately the 100 and 200, and be above the density line, 30 sieve. But then the 3/4 still can be a little out, but still much closer to the 0%, the zero voids line. And the 8 to 18 chart, a lot more in, but it's not complete in. Notice that the 16 and the 8 sieve will almost always be down here out of mid. That research is kind of showing that that's not really a place that we need to worry too much about if they're down out of the 8. But your 3/4 should be here around 20% or so. If you have something that looks like this, you're all right. Okay. Sharing data. Okay, in this the program, the spreadsheet that hopefully everybody has. By entering your material properties, your concrete and aggregate sources and the specific gravity. Enter your admixtures. And enter your aggregate properties. This is where it kind of gets critical with this spreadsheet, and I'll go over that in a minute here. And then cementitious and aggregate proportions. What percentage you have. You can, and this is a real nice feature of this spreadsheet, that you can, if you have 3 aggregates, using a 57 and 8 and a sand, or 3 other, whatever aggregate you're using. If you have three aggregates you're using, you can use this gradation calculator. I'll demonstrate that in a little while, but it's a real nice, real handy tool to use. Excuse me. To give you, what position that you want to get where you want this in the graph. I talked about the aggregate analysis. Say you have the aggregates. You need to, if you aren't already, you need to start putting in all of these these sieves. On a 57, the 3/4 and the 3/8 aren't required, but if you don't get data and put it in, actually is, you won't get what your actual your plot. It won't plot right in the right place. The states is particularly critical, but the 3/4 also affects things. But you really need to start putting them in if you haven't already been. Okay. Other specification requirements of the pilot spec, 1,000 psi with 500 over design. Designing with 7% air instead of 6% air now. There's a 5-inch maximum slump in the field. Ability max is 2,000 coulombs at 56 days. The shrinkage max is 500 microstrain at 52 days after 14-day wet cure. The 1.3 28 7-day ratio in a spec with a 1.2 ratio minimum. The 14-day wet cure with the 7-day spray cure is in there. Cylinders, we're going to break cylinders at 3, 7, 14, 28, and 56 days. This is to gather data. Thinking about some things as far as 56 days. Specification requires the use of a vibratory attachment bidwell roller assembly. This is to get a better finished surface so that we don't have to finish it. Hopefully don't have to touch the surface after the bidwell as little as possible. And this is a pilot. So we want to do all of the projects that we committed to do. Whether we can make all these specifications or not, that's part of the pilot. If we have a problem making this specification, then we kind of want to know that. I was also asked to talk a bit about permeability and shrinkage specification. The new requirement is 2,000 coulombs and 500 microstrain based on after 14-day wet cure, 3-day microstrain after 14-day wet cure. Pilot specification, the original specification that we put out there, I don't know how it got dropped, but original specification gave the DME the ability to approve designs that exceed the maximums limits on a case-by-case basis. And the reason for that was the percent of the permeability test is 42% for a single operator, 51% for multiple operators. The average of 3 is 42% for multiple operators. So the test itself is not super accurate. So saying 2,000 coulombs, you could have a mix that has good ability, but tests outside the 2,000 coulombs. It's kind of the same thing for the microstrain. But we want to gather the data since it is a pilot, and figure out where we need to go. Thing of permeability. Long time ago, this too started permeabilities, and before we started, the average permeability was around 4,000, and after it was below 2,000. But we had permeabilities in straight cement mixes that were 6,000 plus coulombs before we started, because I say 6,000 plus because the lab here stopped the test before the entire period for the permeability test was over because they were afraid they were going to break their equipment. So in straight cement design, you can get really high permeability. We're doing better even if we don't get the 2,000. So that's kind of where that whole thing is. But yeah, for me. you want to go to Justin?
All right. Thank you, Neil. My Justin Bryan with Bryan Incorporated. I'll did some aggregate optimization work and shrinkage testing as the bridge deck cracking protein. Just wanted to take a little bit of time to kind of update everybody on what we've seen. I've done several presentations, so many of you may have heard bits and pieces of this, but kind of want to go through some of the data information that we had. The aggregate optimization, and Neil pretty much summed it all up. Our goal was to work with PennDOT to better understand tracking, specifically on the material side. Important part is we worked off of AAAP, which was a good baseline because we knew AAAP was performed well in the field. We took that mix, worked from there to look at using aggregate optimization as an improvement. The wormed at a research center in Pittsburgh. We worked with Rich Uha in District 11 here on the specific developments of the design. Rich, we went back and forth on what mixes we wanted to see, what versions. That was a nice process to have him here working in hand with us. One that we always try to do anytime we do a research project is implement a practical approach. We're a producer out here. We see mixes and materials different in the lab, but we also have the opportunity to see them through the plant and in the work that we do. We try to keep that practical mentality with the design work and research that we do at the research. A rundown of the mix design series. We ran a bunch of different mixes. These were the main designs that we looked at. Many of them were run multiple times as a comparator for other designs. The AAAP was a standard design that we use on a daily basis. Looked at a AAAP, the same cementitious, same slag replacement with blended aggregate. Also looked at it blended differently, and we called it the optimized aggregate, and I'll show breakdowns here in a minute. And for comparison purposes, we ran a max cement, which was 690 pounds straight cement, and high cement, which was 8 pounds. Just to give us some comparisons in the impacts of high cement. The base mix that we ran, which was our standard AAAP, 600 total, cementitious, 5% slag replacement, 4-5 cement ratio, and we matched airs and slumps between all the mixes. The unification between these three aggregate blends was the coarse aggregate volume and the specific blend. Again, mix 10 cubic coarse aggregate is something typical for this mix. We like it because it has excellent pumpability. This mix here, we didn't utilize any aggregate blend, but AAAP design use a 50 aggregate that's a little bit finer than normal, which the ability have a nice mix, a nice blend. But this is something we use on a daily basis and have several projects with this mix in it. At a blend with keep 10.5 cubic feet, we blend number 8 aggregate. This 7s that we use on this design is a pretty tip gradation, and we want to keep the coarse aggregate volume at 10.5 cubic feet, blend in a portion of number 8 aggregate, and you can see where the box is, where the crosshair is on the box. Still great pumpability and a real nice mix for the Triple. Now the nice mix, what we did, we bumped the aggregate volume to 10 1/4 cubic feet, all blended with number 8. This crosshair down right inside the box in the location. Now this pumping is still doable, a little bit more challenging, but this gets right inside the box. And then we compared these three mixes as far as free restrained shrinkage, air compressive strength, and so we did max cement at 660 cement, and the high cement was 8 pounds straight cement. Both of these mixes had 10.5 coarse, 0.45 water cement ratio. Air and slumps were the same, 6%, 7 1/4, and we held the 6%, 7 1/4 slump for all the mixes. That's what we run. We start for the 7% air. All these have 6% air and around 7, 7 1/4 inch slump. So range shrinkage. Heard various presentations before. Range shrinkage test, without going into too much detail, based on the ASTM, there's a steel ring on the inside. We have strain gauges up for the strain on the ring. Outside of the ring, we cast concrete. As the concrete shrinks, its tension, or actually compression on the ring as it shrinks. The strain gauges will measure the compression, and we turn it into a micro strain value or a strain value to determine how much shrinking. The first we did make a modification to the ASTM, increase the diameter of the concrete ring. It's an 8.5 diameter, and they required you to wet sieve out everything 1/2 inch and larger. We don't do that, obviously, because we really wanted to look at the impacts of aggregate blends in the concrete mix. So increase the concrete ring diameter is 3-inch annular space, and running some. We soon found out was that at that thickness of ring, the concrete didn't crack a reasonable amount of time. I think we ran the first one out for like 6 months and cracks in it. So what we started to do was look at adding control joints on the inside of the ring to help induce cracking. It seemed to work very well, and we compared everything to rings with 4 control joints. So everything's the same. We're not comparing any mix with any control joints to control joints. Everything was held consistent as we got to that point in the study. So reducing time to 24 hours, also in an effort to reduce crack and get some turnover in the ring. Some of the data, the orange line you see is the high back 800 pounds straight. You can see that cracked early in the strain development. The green line, the maximum, which is 690 pounds straight cement, and the blue line, the AAAP optimized. So that's a pretty stark improvement. High straight cement mixes. Here is the 3 blended aggregate mixes. The blue line is the controlled AAAP with no blend aggregate. Green line is the blend, and the orange line is the optimized. It's 11 1/4 cubic feet. So you can see improvements with the aggregate blends as far as shrinkage. Not as significant of an improvement as a reduction in total cementitious when you compare it to 90 and 8 pounds. Well, we can see 157. The only modification we made to that method was we wanted to match the shrinkage testing what we were doing with restrained shrinkage. So cast the beams 4 hours like we did the rings, then begin testing on them right away to make sure that everything was comparable as occurring in the duration. So again, shrinkage data, the purple line, 800 pounds straight. The line is the maximum at 90 straight, and the AAAP with 600 total cementitious, 35% slag replacement. That's a substantial improvement. Where we're at with AAAP. Just wanted to go to cement mixes to see kind of how it stacked up against the AAAP, and we knew AAAP would be a big improvement. This three blends. The blue line's the standard without a blend. Line, the 1.5 cubic feet, and the orange line is the blend at 11.25 cubic feet. You can see improvements with aggregate blends. Again, not the huge improvement that we saw with the big reduction in total cement, but they all perform well. They're all low 500 micro. You know, the blue has no blended aggregate. The green was, if you remember, the ag blends above the box, and the orange line would have been right in the middle of the box. So we did improvement, but they performed really well. They were all very workable mixes. And the AAAP blend would be excellent pumping mix. And the orange line would still pump, but they didn't create a box. That was perfectly optimized. Some conclusions from this. Working on a full report with commentary on everything that we worked towards. Once I get that wrapped up, I'll get that to Rich. He'll be able to distribute it to the group. Just some conclusions. Aggregate blending does improve shrinkage. We saw that. Not nearly as much as the reduced cement factors, which was ultimately the goal of AAAP. So, you know, we're light years ahead of where we were, 10 years ago with bridge deck concrete, and we're looking at ways to, improve it from there. But again, the big jump was to get the total cementitious down and utilize the percentage of pozzolan. Materials in this study were local to Western PA. Some more work could be done with materials from across states, and that's an important component. And we still, consider, and I know the department is design and construction and how, with blended aggregate designs, all facets of the bridge deck are working together to give PennDOT and the Commonwealth an excellent product used in the field. So that I will throw it back to Neil. I know he wanted to do a little demonstration and then field any questions.
Okay. This is the spreadsheet that Mr. Sullivan wrote. I set up here with three aggregates. If you're trying to do this with two aggregates, kind of like good luck to you. But
Neil?
Yes.
You're not your desktop.
Oh, I'm not. I gotta share it again. Okay. There you go. Okay. All right. The sheet that John Swalligan wrote. I have it set up with. The aggregates here. You have to do this if you're going to use this calculator on the lower right-hand corner here. You have to have three aggregates. Doesn't work yet with 4. We might work on that if there's a need. But I have set up so that it's at 60 and 35, which is right in the middle of the box. You change this if you wanted to do 55 and 35. You do that, and you say enter, and it moves it over there. The really nice thing about it is you can go over here, and it shows you on this factor tab where you are in relation to all the boxes that I showed you earlier. Nice. The other thing you can do is, this is 41.2, 18.3, 40.5. You can make this, maybe 42. Nice round numbers, 18, and make it all, and this 40. Make it all round numbers and see where that takes you. Right. And you can go over here and see where you are here. That's kind of what I wanted to demonstrate. Back. You want to go back to 60. You can do that. It shows you what it is before. If you enter it and you say enter blend, and it moves it over there. It really allows you to pick anything you want to do. So it's a real nice feature for this thing, but it only works with 3 aggregates, and right now. But that's, I think, what most producers are going to be using. If there's a need for 4 out there, let us know. We'll see what if on to doing it with 4 or not. So and that's all I wanted to do there. I wanted to show you some of this quality of this program. It really play around with it, see what you think. Feedback. That's all I guess we should ask, are there any questions?
Everybody should be unmuted. If they had questions, they can ask Neil.
Justin Bryan gave his presentation. What kind of aggregate did they use? What kind of stone was it?
This is a limestone. The contrix was rear line typically used. The other stone was Allegheny Minerals. And 57s, and then the 8th was a blend of gravel.
Well, I have my question is, by 7 and 8 grade without having to blend a second aggregate? Is that?
Well, what you'll have to do with that is, when you enter them, you'll need to play around with over here. You play around with the aggregate blend area here. You see where I'm pointing there?
Yeah.
Yeah, you have to play around with that until you got it to where you want it to be. That's all. I mean, 60-40, and then play around from there.
Sure.
Thing. And that's, I'm not available right now. That's, it would have to be an awful coarse, fine aggregate for you to get it in the box, I think. But, it's possible.
What's the theory behind the modification of ASTM 157 with the 14-day wet cure?
I'm not sure. Well, that's one of the things we need to really kind of evaluate during this pilot program, which is why you have problems making the 500 micro strain. We'll all work together on it and see where we go with it, because that's the one thing, you know, we probably ought to be doing things in accordance with the ASTM. If we're not, we need to do some experimental work before we kind of go there. The original idea was that I think that it was to match the work-year regime that they built. So I'm going to get an idea and bring the file in here and go from there.
Neil, this is Kevin Nagy. It's kind of like what you just said. It was 14 days to simulate they're in the field. We gathered whenever we worked on our HPC mix with Dr. Kowski. That's where it came.
District 2, questions. Number of cylinders we're going to mold. You want to use the AT?
Yes, we do. Just to see where.
We recommend water and optimized mix. Water cement ratio are going to be lowered.
Depends on the mix, but yeah, that's a possibility, and it's not a, you know, there's less water demand with an optimized aggregate mix.
Right.
You know, that's a possibility with the mix. It depends on all the components and, you know, how it's out, but yeah.
The other ones with 500 pounds. Is that going to?
I didn't get that. I'm sorry. Could you repeat that?
So for the 4-pound design, is that going to cost 55 pounds? Relate 1,000 plus.
You had to repeat with what? I'm sorry.
7 PSI plus 6 designs, and that wasn't our goal.
Right, and that's the thing. That's why I'm kind of, yeah. But no, we're not using a cap on anything because, you know, there's a minimum and max for cement. But no, that we're not really looking at it that way. Isn't the issue. It's, you know, the properties of the mix are the issue. If you're getting real high, like that, you probably really ought to, you know, producer and PennDOT ought to be looking at the amount of cementitious in the mix and, you know, see where you are there. Maybe able to, you know, reduce the amount of cementitious and still get strengths you need with, you know, with low shrinkages and low sink permeability. So.
One last question. The 14-day wet cure, which we've been doing for quite a while.
Yeah.
Spray cure, is that mandatory? If we're sealing, we have to let it 58 days before we seal it.
Yeah, by the specs, right now it is. It's the put again. So if there's an issue with the going with the Sunday spray cure, we'll have to deal with it. Oh, and during my presentation, I forgot to tell you to send issues Bob McGowan, District 4. If you have any, problems, issues, data, that kind of thing, gather in one place.
Hey, Neil. Ken, you had mentioned Bob McGowan. Is it Bob or Harold Hill that you should go to?
Yeah, you can. I'm sure you can send it to Harold Hill also, but I'm just this materials engineer in his district. I've said to send things to him. So.
And I wasn't sure. And some of the connections haven't been great. I wasn't sure if it was a specific district question or just about anything that was going bridge deck tracking. So, okay, thanks.
Hey, Neil.
Yeah.
It's Bob McGowan. Any questions in my district from and Harold?
Gil, this is Harold. I didn't get a chance to vote. My thought was that whatever district they have questions in, they should send them to their respective DMEs in those districts.
That's fine, but we probably got to have a central place gather all that stuff so that we can, have it all in one place for the group to evaluate.
Well, once the DMEs in the district get it, they can forward the information to me, and then I'll put it on our cracking.
That was the idea. I just probably said it badly.
Okay.
Anybody else?
Who is the central point of contact to collect the information?
Well, what we're just talking about, your DME, your district materials engineer, will be where he would the information, and then he'll send it on to the Harold Hill for the,
Okay, so Harold Hill is going to get copies of all of the data. That's fine.
Essentially, yeah.
I had a question on the design error of 7%. Does it carry over into the portion 2 that you're targeting 7%?
It does.
No, so on the project, it's 7 plus or minus 1.5.
Yeah.
If you design to meet the course factors and so forth from the chart, and your gradation changes when you're actually going to run the material in the mix, can you adjust that mix to bring it back into compliance with the chart without doing additional testing?
Yeah, that's part of the spec that as you go, you're supposed to be, when you get new aggregate and you naturally do a gradation on it, if that gradation, the gradation of the last 5, average gradation of the last 5 tests you've done, change, then you put those gradations, that change gradation in here and adjust as needed.
Okay.
The chances are, though, that you're not going to get a huge swing that will really affect, your box, whether you're in the box or not. If you have to deal with that with the district materials engineer, and it should be a huge deal. If it is, then we'll have to go.
Thank you.
there's nobody else, I think, thank you for, attending. Hopefully this all goes well and we'll be happy we did it, so, anyhow. See you.
Thank you.
Thank you. Bye. What did you say there?